So we're continuing with Gaussian elimination, augmented matrices, and row echelon form. The purpose of this video is to put them all together and a little bit of a short note or explanation of what we've been doing on this. So what is Gaussian elimination? Gaussian elimination or row reduction is using the three row operations, which is, what are the row operations? Multiplying a row by a constant, putting it back in the row, adding a constant multiple of another row to a row and putting it back to that row, switching two rows. And so Gaussian elimination is to use these operations to create a leading one for each non-zero row. And we discussed leading ones a little bit before also. Row echelon form is what you get as a result of the Gaussian elimination. What we're interested in at this point is to actually use Gaussian elimination to solve systems. To be able to do that, we have to start with a augmented matrix. Again, Gaussian elimination can be done both on the system or matrices, but it's much easier to actually get rid of the variables, get rid of the operations and the equations, and just use the augmented matrix to do Gaussian elimination. So again, the plan is to use an augmented matrix, and we start with a matrix of, we start with a system of three equations, three variables. An augmented matrix for a matrix of three variables, three equations will look like this. This is an imaginary line. These are the constant coefficients of the x, y, z, and these are the constants that sit on the other side of the equations, on the right side of the equations. So an augmented matrix for a 3 by 3 matrix, 3 by 3, three systems of three equations, augmented matrix of a linear system of three equations and three variables. And so this part is the coefficients, imaginary line. For example, if you're plugging it into your calculator, you don't have to put that line in. Constants. Matrix of coefficient, matrix of constant, or vector of constant, depends on which one you want to call it, and then imaginary line between them, so you attach them together and then you perform the row operations on them. And so another discussion that we're facing at this point is that how many different row echelon forms are we going to get? Because depending on the format of your row echelon form, we're going to have different type of solutions. So that's again, general, if you take this is what? This is a 3 by 4 matrix. If you do Gaussian elimination on any 3 by 4 matrix, you will get different type of formats of row echelon form. But we're in here, we have a specific 3 by 4. 3 by 4, that is an augmented matrix for a system of three equations, three variables. That means that at least one of these values in the first column is going to be non-zero. Therefore, there are more options if you are allowed to have all zeros in here for row echelon forms, but we're not going to discuss those. So I'm only discussing when at least one of the values in this first column is non-zero. And so let's go, let's discuss this one. At least one of the values in each column is non-zero in the matrix of coefficients. So what are the choices that we can get if we do reduce row echelon form? The most famous one is when you have a unique solution. So in a unique solution setting, you have obviously the first one of these has to have a leading one, and then could be other values, then zero underneath the leading one, and then the next leading one comes one indented. And then the next leading one is there, and it comes in one intended. So this will give you a unique solution. Unique solution. Is this the only way to get it? No, we have solved enough problems to know that there are other ways of other formats for this. So the other one, again, starts with a leading one and the imaginary line. And then the second leading one is two indented. And then now there are multiple options. The last row could be, there could be no leading one, and I could be all zeros. Or the other option for this is that the last row has a leading one. Case one gives you infinite solutions. And we're going to give an example right after we're done discussing all the different formats. Case two, and how do I know? Because I have to rewrite this in the system format. And I know that all the coefficient of x, y, z is 0, but it equal to constant 1. So this gives you 0 equal to 1. So this is inconsistent. Is this all that we can get? No, there are other options. What are the other options? One way is that it's possible that for a system we're completely, with the first indent, the second row completely gets indented until the end. So that's another one. And so 1, star, star, star again. The first row is given. Then instead of one indent is always given, second indent sometimes, and I get a third indent. And so this is again is going to be 0 equal to 1 in this row, and so it's inconsistent. What are the other options? What if the second row just gets one indented? What are the options with that? So first row again, as usual story. Again, because it's a system, first row is always the usual story. The second row comes back the same way as just one indent. And then what are the options for the third row? One option for the third row would be that the third row is all zeros, no leading one for the third row. Okay. The other option for the third row, so again, I'm rewriting this. So basically what I'm doing, I'm playing around with all the options I can get with these matrices and telling you what will give you what answer. This one, I have two leading ones and a row of zeros. If you rewrite the system, you will get infinitely many solutions. So again, infinite. And the next one, again, you get 0 equal to 1, and that gives you no solutions again. Inconsistent. So far we categorize all the different formats that we can get. Not all of them. There's one more that is left. We categorize a bunch of formats that we can get by using the Gaussian elimination on an augmented matrix of a system of 3 equations and 3 variables. The only one that I didn't put in here is that would be related to this. We can have the first row going, and then no more leading ones. And this one also gives you an infinite solution. This is a result. This results from if all the equations in the systems are constant multiple of each other. So the next thing that I want to do is we want to discuss the fact that if you look at the row echelon form of your augmented matrix, you should be able to see if a system is inconsistent or not. How do I know inconsistency? These are the signs. If I see a row that is all zeros in the area that coefficients live and 1 at the end, that tells me the system is inconsistent. So how many of those do I have? One over here, another one down here, and another one over here. So these 3 systems are inconsistent, and by looking at the reduced row, by looking at the row echelon form, you can see very easily. So what are the other options? The other options that I have are this one, which gives me a unique solution. This one, which gives me an infinite solution. This one, again, that gives me an infinite solution. And a fourth one that gives me infinite solution. Another thing to notice, the first one has 3 leading ones. That's why it's unique. The second one has 2 leading ones. Third one has 2 leading ones, and the fourth one has 1 leading one. Basically, the first one, the solution to the first one is going to be a point. To the second one is going to be a line. Third one, another line. And the fourth one is going to result in a plane, which is any of the planes in that the equations are representing. So in the next part of this video, we're going to give you an example of 1, 2, and 3, and 4, and one example for each of those situations. We're going to skip the system and how we how we do Gaussian elimination. That's another part of the lesson. We're going to just assume that we've done the Gaussian elimination. We arrive either at any of one of these four options, and then we solve the system from there. So we're continuing with the four options that we have with the row echelon form, in examples of each one of them and how to solve if you get one of those. So the very first one was that each row had a leading one. And so this is an example of that. See, leading ones are there, and then you have, for each of the entries that are star, you can get a number. That number can be 1, 2, but that would not be a leading one, by the way. And you can get zeros and et cetera, et cetera. So how do I solve this? This has a unique solution. Why? Because if I rewrite the system that comes with this is going to look like, so the system that comes with that is x times 1 plus 1 times y plus 0 times z equal to 0. Then I will have y plus 4z equal to 0, equal to 10. Then I will have no x, no y, z equal to 3. It's a back substitution method, so z equal to 3 is given. Going back in here, I plug in 3 for z, and I get y plus 12 equal to 10, which gives me y is equal to -2. Then again, use this, and in this case I don't need to use z equal to 3 because there is no z term in this equation, but normally there are plenty times that you actually use both of them, and you've seen some of those examples before. And so I plug in y equal to -2 in here, and I get x minus 2 equal to 0, which gives me x is equal to 2. So the solution to the entire system is the unique solution: x equal to 2, y equal to -2, z equal to 3. So that was the unique solution. Let's look at something without a unique solution. The first thing that I usually recommend is rewriting the system that this row echelon form represents. What does it represent? Again, x for the first row, so it's x plus 2y plus 3z equal to 5. The second row gives me 0 times x times 0 plus 0 times y plus 1 times z equal to 7. And then the last row is 0, so I don't have to rewrite that. So the system has been reduced to 2 equations. Here, when we had unique solution, there were 3 equations, 3 restrictions in your 3-dimensional world. Here I have 2 restrictions in my 3-dimensional world. Now, the next thing that I always recommend, when you see that the number of equations is less than the number of variables, you know that you have infinite solutions, so you will have to assign variables. How do I assign variables? Again, little side note, this was the column of x, this was column of y, this was column of z. Go back and find the column that does not have leading 1. X has a leading 1 in this column. Y does not have a leading 1. Z has a leading 1. Any variable that does not have a leading 1 in its column, assign a parameter to it. Are there any other ways of doing this? Yes, there are. But this method of bookkeeping of assigning parameters only to the variable without leading 1 makes it much easier when you have to assign multiple variables. So start from systems of 3 equations, 3 variables, and continue that way. So I'm assigning t to y in here. So how does that work? That means that y is going to be equal to t. Now, in this specific system, z was solved for me. Now I have y equal to t, z equal to 7. As usual, you back substitute into here. And as a result of back substitution is x plus 2 times t plus 3 times 7 equal to 5. And be aware of your t's. They can get messy very quickly. So in here, now I have to solve for x. That means that I have to subtract 2t and 21 from the other side. So it gets x equal to 5 minus 21 is negative 16 minus 2t. So the solution to this system is x negative 16 minus 2t, y t, and z equal to 7. One parameter, it means a one-dimensional object in 3 dimensions. That is an equation of a line. Infinite solutions. That means that any point on the line is a solution to that system. So the third option of the formats that we discuss of row echelon form is this one. There is a leading 1 for the first row for x, leading 1 for the second row, that's for y, and then no leading 1 for z. So this could be an example. Leading 1 for x, leading 1 for y, everything else are numbers. It could be zeros or ones as long as we have the discussion is over leading ones. Now, again, the first thing that I recommend is rewriting the matrix into the row echelon form of the matrix into a system. So that is the first step. X minus 2y minus 3z equal to 5. The second row, no x, y plus 5z equal to 7. And the last row is just 0 equal to 0. Again, there are 2 equations and 3 variables, so the number of equations is less than the variables. There are fewer restrictions on the solution. Therefore, we have infinite solutions. And so the next step to do is to choose the parameters because there are infinite solutions. Again, little side note, this is the column of X, this is column of Y, this is column of Z. There's a leading one for column of X, and then leading one for column of Y. No leading one for column Z, column of Z's. So Z, we assign a free variable to Z. So this will change things to Z equal to T. As usual, we back substitute. In here, I put Z equal to T to solve for Y. Y plus 5. T equal to 7, and it gives me Y is equal to 7 minus 5t. The last step is to back substitute Y and Z into the first equation. So, and this gives me X minus 2 times 7 minus 5t minus 3t equal to 5. And now solving for this is X minus 2 times 7 minus 14 plus minus 2 times 5t, which is going to be 10t minus 3t equal to 5. Subtract to get X is equal to 5 plus 14, that's 19. And then 10t minus 7t, minus 3t is 7t, subtract 7t minus 7t. So that's the X value. And the solution to this is going to be, and I'm kind of running out of space, so I'm going to write it above that. The solution is going to be 19 minus 7t, 7 minus 5t, and t. Infinite solution again, and there are, and this is an equation of a line again because we have only one parameter. The last problem to do is number 4. So let's check that the format matches. So I have 2 rows of zeros, one leading one, and then in the row with the leading one, all the rest of them can be numbers. First step that I recommend is to rewrite this in the format of a system. Oh, this one is very short. Why? Because only one equation is involved. That's why I'm saying that all the rest of the equations must have been a constant multiple of this one. Now, knowing that this is going to give me infinite solutions, how do I write it in a parameterized form? Look at, again, X, Y, Z, column X, column Y, column Z. And then the next step that I want to do is to make sure that any column that doesn't have leading one, X has a leading one, Y doesn't have a leading one, and Z does not have a leading one. So I'm starting from Z, I assign T to that one. I need another parameter name, S to this one. So now I have Y is equal to S and Z equal to T. What have I not solved for? I have not solved for X. So let's plug it back into here. And I get X plus 3S minus 4T equal to 5. That will give me X is equal to subtract 3S and negative 4T to get 5 minus 3S plus 4T. So the solution to the entire thing will look like 5 minus 3s plus 4t s and t. Okay, notice that we have two parameters in there. Therefore, our solution is two-dimensional in a linear object in two-dimensional linear object in 3 dimension is a plane. And so this describes all the different formats that we can get for the 3 equations and 3 variables.